Yes. Okay, then I would like to ask you, Shesha, to start with a kind of introduction of you and your colleagues before you go to the topics, please.
Yeah. So, hello everyone. Good afternoon. It's afternoon in Europe, and a good day to whoever is joining from outside. My name is Shesha. I'm a PhD student at the University of Luxembourg under the supervision of Professor Massimiliano Esposito. And we mainly work in non-equilibrium thermodynamics as a group in various systems. And I would like to thank the organizers for inviting me to present our recent work on asymptotic growth in open chemical reaction networks. This is work I did with Francesco Avanzini, who is currently in the University of Padua, and Massimiliano. The work is published in Physical Review E, and please feel free to write to me for any sort of clarification. So I hope my pointer is visible.
Yep.
The outline of the talk, I will start with a motivation and a problem statement, and then I'll introduce the formalism, which is the dynamics and thermodynamics of open chemical reaction networks. And then I'll discuss the results and end with a few prospects. Yeah, please feel free to interrupt me at any point with questions. So the title of my talk had growth in it, and I sort of want to highlight in this slide that growth is sort of a very common phenomenon, and especially in the chemical context. I put two examples. This is the biochemical context, if you wish. I put here in this slide two examples of growth, and we all have this intuitive idea of growth. You have a system, and there is something in the system that is accumulating. If you take the first example, this is a polymerization process. On the left, you see like basically monomers, and after some time, you see the formation of long chains of polymers. And in fact, you can track them. These are very old known things that this quantity here is the average length of the polymer in the solution. And you can see that it increases in time. So in this case, the variable that is growing, if you want, is the length of the average length of the polymer. One could also take a look at biology. And of course, there famously, we have population growth. If you start with a population of cells, the number of cells, and within a growth medium, we know the number of cells increases in a very well-known way. But even within a cell, if you just look at the cell cycle, then the length of the cell, the number of proteins in the cell, all of them increase over from the time of cell birth to cell division. And in fact, it is known that this increase is exponential. Here is something, here is a graph I took where they were measuring the protein count in cells. And you can see that the exponential is a very good fit for this. Was there a question? I'm sorry.
No, just some noise.
Okay. So now the thing that I'm interested in for the purpose of this talk is deterministic chemical reaction networks. And we want to think about concentration growth. So that is an accumulation of concentrations. And people have studied this a lot in the past years. And I want to, as an example, I want to show two models, which are sort of related to the physical systems I showed in the first slide. So the first model is something called non-enzymatic template replication. And the idea is that you have a template C, and you want to basically copy C. So you want to make multiple copies of C, starting from A and B, which are like monomers, basically. And the way this works is that A and B, along with C, they form a complex, this complex here. And then this complex, and then you can see that a bond forms here between A and B, creating two copies of C. So this is the dimer C2. And C2 then splits into two copies of C. So the whole reaction is autocatalytic. And the set of reactions are written down here. So you have the formation of ABC, which then goes to C2 and 2C. And this is actually very, very old work. And people were interested in asking, how does the concentration of C increase with time? So it's not just C, it's the total template concentration. So you look at C ABC and C2. And you ask, how does this quantity increase in time? And in fact, it is known that this quantity scales parabolically in time. So this is called parabolic. And one thing I want to highlight here is that this reaction, the second reaction, is sort of seen as irreversible. So this is again like the polymer example. Whereas a second example comes from the Hinchell-Wood cycle. And this is a model people use for basically exponential growth in cells. And the idea is that you have species X1, X2, X3, and so on. And X1 catalyzes the formation of X2, X2 catalyzes the formation of X3, and so on. And here is my very bad drawing of this cycle. I use dashed lines to indicate that all the reactions are irreversible. And in fact, if you look at the concentrations of X1, X2, X3 as a function of time, all the quantities are suitably rescaled, you will see that there is actually exponential growth. So here I've taken plotted log of the concentration versus time, and you see it's linear, so there is exponential increase. And people have also studied this in the stochastic regimes and so on. Now, our interest in this comes from the angle of thermodynamics, right? So, of course, the dynamics is very important. It's important to ask how things scale in time, but it's also important to ask if we can associate notions of cost. How costly is it? Like, is parabolic growth costlier than exponential growth? Or is vice versa? Is exponential growth costlier than parabolic growth? Or notions of efficiency? And the right framework to do this is non-equilibrium thermodynamics. So equilibrium thermodynamics, the theory that we all study in university, came from the study of changes. And it was only in recent years that we understood at the stochastic level how to think about non-equilibrium systems and how to characterize how far away they are from equilibrium. And using these ideas in recent years, a lot of work in our group has focused on developing non-equilibrium thermodynamics for macroscopic systems. So you have deterministic chemical reaction networks, and they are out of equilibrium. I will make these notions clear in the formalism aspect. And they can show complex behaviors, right? They can show patterns, they can show limit cycles, they can show multi-stability. And these thermodynamic notions, they help us assess the energetic cost of this. How much energy do you need? How much cost do you need to pay to sustain an oscillation or a pattern, and so on? So now that the framework exists, it is very tempting to say that all we need to do is to just take the framework and apply it directly to the models that I was showing you in the previous slide. The problem with this is that, firstly, thermodynamically, every reaction has both a forward and a backward, whereas in the models that I showed you, all of them were irreversible. And this is the case for many models that you will find in the literature. So this is one problem. And second problem is that the theory of non-equilibrium thermodynamics that we have relies on elementary reactions, which means that the law of mass action should apply. Whereas typically the models that people write, for instance, like these cycles, they're typically coarse-grained, as in there are multiple steps happening inside, but effectively the net process is that X1 helps create X2 in this example, for instance. So one can ask the question, is concentration growth, and by this I mean is accumulation of concentrations, possible in chemical reaction networks where all reactions are reversible? And the answer is yes. And this was shown by Francesco in this JCP paper in 2022, where he was studying this chemical reaction network. And the key ingredient here, which I want to stress, is that you are thinking of a chemical reaction network that is open. And by open, I mean species are also being exchanged with the environment. This chemical reaction network, let me first introduce the chemical reaction network. So actually what is happening here is that you have a fuel and you have a waste. And these E, EF, AW, they're all enzymatic species. And so effectively, E is reacting with F to form EF in the first reaction. This EF is creating EW, which is then degrading to form E and W. Similarly, EF can react with some substrate S to form a complex, which then degrades into EW and product E. And the species colored in green are all being exchanged with the environment. One thing I want to stress is that all these reactions are reversible. Although I've indicated a net direction in the diagram, they are all reversible, and I've chosen the direction arbitrarily. So every reverse reaction exists. Furthermore, every step is elementary. So the law of mass action applies to every step. And in this case, what Francesco was studying in this paper was how you exchange F, W, S, and P. Well, different methods of exchanging cause different asymptotic dynamics. And the answer turned out to be true, that indeed, if you exchange things with the environment in a certain way, you can have this accumulating phase that I've plotted here in this plot of concentration versus time. And you can see that there is a linear increase in the concentrations of F and S in this example. And this we call asymptotic concentration growth. So I want to stress that this is asymptotic. So this is a large time thing. And secondly, it's a behavior that we see in open chemical reaction networks. And now we can ask the questions that we want to answer. When does this growth occur? So that is not trivial, because it is not that the exchange is made in a way so as to create this. There are methods of exchange in which you will not see this and you will relax to its point. So when does growth occur? That is the first question one would like to answer. And when the chemical reaction network shows growth, the second question you can have is how will the concentrations scale with time? And what does the thermodynamic formalism that I introduced say about the cost of this growth? So these are the three questions that I will try to answer with my talk today. So I now move into the formalism. And yeah. So as an example, I will always use the Michaelis-Menten chemical reaction network. So we have a substrate S and an enzyme E. They react to form the complex ES. That's the first reaction. And in the second reaction, ES splits into E and P. It's a very simple reaction network, but it serves as a very good example to get intuition. So formally, we define a reaction in this way, where alpha is the vector of species. So it's E, ES, S, and P. The vectors nu plus rho and nu minus rho, they count how many number of each species participate in a reaction. And the difference between nu minus rho to nu plus rho, this is a column of the stoichiometric matrix. So in the first reaction, you are consuming E and S to create ES, and of course, in the ratio 1:1. An important topological feature that we will need are conservation laws. So they are vectors in the left null space of S. And importantly, I will assume that every reaction network that I study in this thing will have a mass conservation. So that is at least one conservation law where all the elements are positive. Now, physically, we think of these conservation laws as moieties. What I mean by that is that they represent groups of atoms that are conserved by the reactions. And that I've shaded in red and blue here, just to make it easy. So for instance, if you look at the atoms or the groups of atoms in S, the same things should also be in ES and P. And that is reflected if you look at the conservation law LS, which has entries for ES, S, and P. Whereas for E, you can say that things in the constituents of E must also be in ES, and that is again shown in LE. So this idea of a moiety will be useful here. Now, as I said before, we are interested in open chemical reaction networks, and we're looking at deterministic chemical reaction networks. So the dynamical variable is concentrations. We define Z, which is the vector of concentrations, and we can cut it into two vectors, X and Y. X are those species whose concentrations change only due to reactions, which are EF and E in this example. And S and P are exchange species. They are species which involve both, whose concentrations change due to both reactions and exchanges. Okay, and the rate equation is given here, where J is the reaction rate, S is the stoichiometric matrix, and together this is the effect, the net effect of reactions. And I is modeling how the species are being exchanged with the environment. And S we can split into Sx and Sy, as I've shown here. You can cut along the columns into Sx and two submatrices, Sx and Sy. And then you get this set of equations for X and the Y species. Importantly, we assume that we are always working with ideal dilute solutions and volume is a constant. And in this setting, all reaction currents, you can write it as the difference of the forward current minus the backward current. The forward flux minus the backward flux. And these fluxes follow mass action. So the current of the first reaction would be the forward flux, which is proportional to the product of the concentrations of E and S minus the concentration of ES, and with suitable rate constants. I also want to indicate that we can define this capital L lambda, which is the dot product of the conservation law with the concentration. And these quantities are conserved by reactions, but they are not conserved due to exchanges. So the derivative of this, we call this the moiety concentration. And the change in the moiety concentration is due to the exchanges. So in the example here, you see that LS changes due to the exchanges, whereas LE, which does not involve the exchange species, is still conserved in the dynamics. And for the mass density, for the mass conservation law, the corresponding concentration, I will call the mass density. So I spent a lot of time saying it's very important that we looked at open chemical reaction networks. So the question is, what kind of exchanges are we looking at? So typically, the way people think of exchange is that you have a reservoir of particles. So if you take this example, you have a reservoir of S, a reservoir of P, and then this exchange is assumed to be very, very fast, such that if S is consumed in a reaction, the reservoir is able to instantly supply S, or if P is produced, it is able to extract it, and the vice versa. So effectively, since this exchange is very quick, we can say that the concentrations of the S and P species should be constant. And these reservoirs are called chemostats. And this is the way we usually think about exchanging species with the environment. And people have ways of creating chemostats. For instance, here there's a system where you have a reaction network, you have two semi-permeable membranes, and then, as I said, you have a stock of whatever you want to exchange on these sites, and you assume the exchange is very, very quick. But you don't need to fix the concentration. Although in this case you're fixing the concentrations, this need not be the only way to exchange species with the environment. And these are the other two sort of protocols we studied. And in flux control, what you do is that you inject species at a constant rate and you extract species at a constant rate. So in this case, you inject S at a constant rate and you extract P in this example at a constant rate. But you could also do the extraction differently. And this is what we call mixed control, where you inject S, but you extract P proportional to how much P is inside. So in the case of flux control, the currents are just a vector of constant values. And the current for IS will just be a positive constant, for IP will be a negative constant. Whereas for mixed control, the influx rates are still constant, but the outflux is proportional to how much is inside. And this you can model by this diagonal matrix D acting on the vector. And these kind of setups are, for instance, in what they call continuously stirred tank reactors. This is a special case of mixed control where you have influxes of different species. So in this network, you have influxes of water, NaOH, and so on. But you have the outflux of all species, and that is this so-called the setup called the CSTR, which is also well known. Whereas in our model, it's a generalization, so you don't need to extract every species. And then the entries of the diagonal matrix tell you the rates at which you're extracting, so only some of them can be extracted. So now I move to the thermodynamics, and here I know this slide has a lot of things, but I will try to be very brief. So there are two main ingredients in our thermodynamic formalism. The first is the chemical potential, and the chemical potential as in equilibrium is the change in free energy upon adding a species into the system. So here, if you take a system and you add, let's say, a particle of S, the change in free energy would be mu s. And you see that it has a standard part, standard chemical potential, and this part that comes from the concentrations. A second and a very key ingredient in the thermodynamic theory is this condition of local detail balance. So this is a condition that links thermodynamics with the dynamics. And this is essential for what follows. And what it says is that the log ratio of, for every reaction, the log ratio of the forward flux by the backward flux must be linked to the chemical potential change in that reaction. So this automatically tells you that you cannot have one of these fluxes going to zero. And this is the problem with irreversible reactions that I was telling you. As as this quantity, you basically need either both to go to zero or both to be non-zero. With these two ingredients, one can write down a second law, which I've put in this box. So in classical or in equilibrium thermodynamics, the way we think of the second law is that the total entropy of the system and the environment must be positive in any process. This quantity.
Excuse me, I have a question.
Yes, please.
I'm close to losing the thread. Is the second law a requirement, an axiom, or whatever? What is it? You suppose it, or you took it from another science, or how is it?
So, I mean, with the given, so if you assume that you have the condition of local detail balance and that you're working with an ideal dilute solution,
that is an assumption. We can say that it's an assumption about the reaction, not about the second law.
We can derive this non-equilibrium second law.
Pardon?
Is that what you're asking? You can derive this non-equilibrium second law. Is that what you're asking?
Yeah, Shesha, if I may make a comment.
Yes, please.
Yeah, please.
So if you assume mass action law, which
Yes.
you assumed before, the second law is a consequence, right? I mean, it's a given the definition of the chemical potential and given mass action law, one can prove the second law.
Okay, thank you. So it's a theorem. Okay.
Yeah.
It's clear.
So as I was saying, so the entropy production, so this quantity, what we call the entropy production rate, this is the quantity that in classical, in equilibrium thermodynamics, which is always supposed to be positive. And for non-equilibrium, we can actually write down what is this quantity, this entropy production rate. And you see that it has the following form. It is the current times this log ratio. And this is always positive. And secondly, it tells you how far away you are from equilibrium. And the idea being that when it is zero, you're in equilibrium. And when it's positive, you are constantly dissipating. This is the amount which you dissipate to the environment. Now, in the second law, so along with the entropy production rate, you have two other terms. The second term, which is, it's a change in a free energy. And this is the Gibbs free energy. So the second term is the change in the free energy, which is the Gibbs free energy. And the first term is a chemical work rate. And what the chemical work rate is telling you is the work you're doing in exchanging particles with the environment. So you see that it has a form of mu times I, where this is the rate at which you exchange particles with the environment. So in this example, you would have mu SIS plus mu PIP. And this is the total free energy that is, this is the total work that is being done by the reservoirs. And all the second law is telling you is that a part of your work is going into your free energy, and the rest is being dissipated, such that the amount which is dissipated is always positive. So I would refer you to these works if you're more interested in understanding how this formalism comes about. One last thing that I have to talk about in the thermodynamic formalism is the notion of an equilibrium versus the non-equilibrium steady state. So if you take a closed chemical reaction network, then starting with any initial condition, you will evolve towards a state of what we call an equilibrium state, which is a fixed point where all the reaction currents vanish And furthermore, the entropy production rate vanishes. So this is an equilibrium state. And I simply simulated the Michaelis-Menten for to show you this. And you see that initially you have a positive entropy production rate, but this is because you're out of equilibrium. And then because the system is closed, you will relax towards an equilibrium state. And in fact, the Gibbs energy, which is the free energy, is the Lyapunov function for this relaxation. But the moment the system is open, you can have fixed points which are called non-equilibrium steady states. And in such example, your concentrations evolve towards a fixed points which we call a steady state. At the steady state, the currents are no longer zero, so you can have a net circulation in your system. And both the entropy production rate and the work rate go towards positive constants. Again, I depict this in this plot. You see the blue curve, which is the entropy production rate, goes to a positive constant. All that means is that because you're exchanging species with the environment, you are at a state that is constantly dissipating. That is the physical way to think about this. And in fact, the origin of this dissipation is that in this example, you can take a particle of S into the system. And if you do the reactions, the first and second reaction, you can create a particle P, which you then exchange with the second reservoir. And in this process, and in this way, you're creating a current between a reservoir at one chemical potential and a reservoir at another chemical potential. And that is the reason you're continuously dissipating in this process. And this is like, if you want an analogy, it is like creating a current between a hot bath and a hot temperature bath and a cold temperature bath. And again, you will constantly dissipate in that example. So with this formalism in mind, now I can fully state the problem. What Francesco was studying was the difference between concentration control and mixed control. And in concentration control, he saw that you will always reach steady states. Whereas in mixed control, what happens is that you can have this accumulating phase. And in this example, F and S were injected into the system, and W and D were extra. And you saw this growth. And finally, I want to say that the way I define growth is that basically I want at least one concentration to continuously keep accumulating in my system. So now I move into the results. So the first question that I asked you was, when does growth happen? And for that, we can actually come up with simple criteria. And the simple criteria is to look at the mass density. You can also look at the free energy, because the farther away, the closer, the farther away you go from, let's say, the origin, the more the free energy increases. So you can also look at either the free energy or the mass density. And if the mass density is increasing, then you have growth. Whereas if the mass density is bounded, you cannot have growth. And for a trivial example, of course, if your system is closed, the mass density doesn't change, you don't have growth. Whereas if you have a tank reactor, like the one I was saying, where you extract every species. So if you extract every species, then you can write down how the mass density changes. And you will see that it obeys this linear differential equation, whose solution is always bounded. So no matter how complex the chemical reaction network inside the CSTR as a setup cannot show growth. And here you see the power of having the mass density as a diagnostic. Finally, in flux control, if you remember, the exchange currents were just constant. This means that the change in the mass density is just a weighted sum of the currents. And as long as this is positive, you will have growth. So every system, every chemical reaction network will grow under flux control, whereas no chemical reaction network can grow with the CST. And that was okay, but we did a more systematic analysis, wherein we considered classes of chemical reaction networks that were dynamically linear. By dynamically linear, I'm referring to the reaction currents. And being dynamically linear, they were simple enough that we could analytically solve them. And we could show that in these classes of chemical reaction networks, you have growth under flux control, but not in mixed and concentration control. Whereas for dynamically nonlinear chemical reaction networks, you can have growth under mixed control, but no growth under concentration control. And I will specify how you get dynamically linear or dynamically nonlinear chemical reaction networks in a second. And just to refresh your memory before I go in concentration control, you fix the concentrations of the Y species. In flux control, you have this, basically you have the reactions, and then you have a constant injection/extraction. And this is just a constant vector in your rate equation. And in mixed control, you have a constant injection, but the extraction is modeled as some diagonal matrix times the current state of the system. So a simple example of a dynamically linear network is our so-called unimolecular networks. So these are examples of unimolecular networks where, by unimolecular, I mean that every reaction just involves two species, and it sort of looks like this. X1 goes to X2, X2 goes to X3. This is a simple example of such a. If you write down the reaction network, it's a simple graph. You can, the mass conservation law has entries 1, 1, 1, 1, 1. And when the system is closed, the evolution is given as follows. You can write down the evolution of the concentration in terms of this W matrix. For those of you familiar with Markov processes, this W is a rate matrix. If you're not familiar, it doesn't matter. The properties of W are very, very well categorized. And it is known that W has all the eigenvalues of W are negative, except the largest eigenvalue, which is unique and is equal to 0. Correspondingly, I call the right null eigenvector of W as the equilibrium, as pi x. And you can show that the equilibrium concentration is given by the mass density at time 0. Recall that it's a closed system, so the mass density is conserved. ln 0 times pi x. So this is the equilibrium state. Now, a first result we were able to show for these systems is that no matter what kind of control you look at, I can rewrite all the types of control in this way. So obviously you notice WZ, which is the closed dynamics. And therefore I'm saying that all the exchanges can be written as DZ plus I. Now this is interesting because for flux control, this is trivial. You just have to take D equal to 0 and I as the vector of the exchange slash, the influx slash outflux. And for mixed control, again, your D just has to be the diagonal matrix D. But for concentration control, this is non-trivial, because the equations I showed you for concentration control, you had to split it into X and Y, and you had to keep the concentration of the Y species constant. So why is this true for concentration control? Well, it's true because, and I can show you that with a simple example. Let's take the reaction network I've drawn here. You have 4 species, X1, X2, X3, X4. And let's assume I fix the concentration of X4. And now if you focus on this reaction, it's easy to see that the forward flux from X4 to X1, this you can treat as a constant because the concentration of X4 is constant. And the reverse flux, you can treat as an extraction proportional to how much X1 is inside. And that means that if I look at a smaller system with the dynamical variables being X1, X2, X3, and I forget about X4, this system would look like this. So X3 would have an injection rate and an extraction rate, and so would X1. So you can map concentration control on this larger space onto mixed control on this smaller space. And that justifies why we can do this. So yeah, so now I'm telling you why. So now that we know this, I can tell you our first result. So for dynamically linear networks, we are, I'm talking about this area where under mixed or concentration control, you don't have growth. And that just follows from looking at the properties of this equation. So once you have this kind of a linear equation, all you need to do is to study the eigenvalues of W minus D. And provided D is not 0, which is the case of mixed or concentration control, you can show that all the eigenvalues are negative. And so your Z will reach a fixed point. On the other hand, if D is 0, then you can see growth. And we characterize this growth very well. So what happens is that all the concentrations increase linearly in time, and they show a very special form. So if you remember, if there was no current, the equilibrium was the mass density at 0 times pi x. Now, what happens is that you can split the evolution into 2 equations. First, the evolution of the mass density, and the mass density increases linearly in time. And the second equation tells you that every concentration is given by this quantity, which is which is like a time-dependent equilibrium to a constant. What do I mean by a time-dependent equilibrium? The idea is that if I shut off the fluxes at time t, this is precisely the equilibrium state of the system. So what is happening is that as you can sort of think of this dynamically as following an equilibrium state that you're pushing away. And you see that at larger and larger times, this vector being a constant is dominated by this term, which is increasing linearly in time. And so it is not very surprising that because you're close to an equilibrium state, your entropy production rate actually decays. So even though you're accumulating free energy, because the amount of substance in your system is increasing, the amount of dissipation is decreasing in time. And in fact, it has a 1/t decay that we can predict exactly.
Excuse me, could you go one slide back, please?
One slide back.
Yes.
Yeah.
Here, ZT tends to something. Is it not a negative vector?
Is it not? No, that's because D has negative entries. So this is the inverse of this operator.
Okay, thank you.
No.
Okay.
Thank you.
There were so many minus signs. Okay.
Yeah, I'm sorry.
Sorry.
Yeah, so as I was saying, we call this equilibrium growth because technically your concentrations are increasing, but in such a way that the dissipation is actually decreasing. So at large times, it is as if you are sitting on an equilibrium state that is moving in time. And we can characterize this. And here in this plot, I plot the concentrations versus time. You can see all the concentrations increasing. As I said, all species grow. And in the dashed blue line, I plot the equilibrium of x1, the time-dependent equilibrium. And you see that at large times, they fall on top of each other. And in this plot, I plot the various thermodynamic quantities. In particular, I want to note that the entropy production goes down in time. So that actually finishes up the story of dynamically linear networks. I've shown that in flux control, they can have growth, whereas in mixed and concentration control, they don't grow. There is a second class of dynamically linear networks called pseudo-unimolecular networks, but I will not go into them due to time constraints. Let's talk about dynamically nonlinear networks. And of course, these are multi-molecular networks, and this is indeed the kind of examples we want to study. And in this case, I don't have broad general results. What I do have are examples of different systems. We studied 4 different systems and have examples and sort of concepts from each system that I will try to illustrate. So one could assume that because the unimolecular system showed this equilibrium growth, one could assume that nonlinear systems will also always grow out of equilibrium. But that need not be true. Even nonlinear, dynamically nonlinear, in this case, multi-molecular networks can grow close to equilibrium. And I show this with this autocatalytic network here. You have a species S that is converting into some autocatalyst E, and P, which can convert into some E star, and E and E star can react to form 3 times E. And the system has one conservation law, and that's the mass density. And in this case, I'm looking at flux control. So we are here, where the influx rate of S is positive, and Fe is being extracted at a constant rate. In this case, again, you see that all the species are growing, firstly. And the interesting thing compared to the previous example was where you had everything growing linearly in time. Here you have some species, in particular E and S, growing as square root T. So you have a nonlinear dependence on time. But you're still growing close to equilibrium. That you can see from the right-hand side of the screen, where the entropy production rate is still going down. And how do we understand this? So the idea is that you can again use an ansatz like the previous example. So depending, the mass density is constantly increasing in time. And for a given value of mass density, you have an equilibrium vector. And you are a small distance away from this equilibrium vector. In the previous case, that distance was a constant. Here, it is subleading. It does not need to be constant, but it's subleading with respect to this. And with this, you can actually derive both the square root T scaling, because all you need to do is to look at the equilibrium of these reactions. And at equilibrium, you see that E is proportional to S. The concentration of E is proportional to concentration of S. Concentration of E star is proportional to concentration of T. But from the third reaction, you see that the concentration of E star will grow as the concentration of E squared. And that is exactly what you see here. You see a square root T and a T. Secondly, with this assumption, you can also show that the entropy production rate should decay and the free energy and the work should increase logarithmically. An important comment to make here is that growth is a phenomenon that occurs in open networks. So you really need to drive the system. But in equilibrium growth, all the free energy that you're putting in through your chemical work is being converted into free energy. Nothing, very little is being dissipated. So if one thinks of a notion of efficiency, this would be close to efficiency equal to 1. So equilibrium growth would have efficiency equal to 1. But multimolecular networks can grow out of equilibrium. And that, again, we go back to the Michaelis-Menten, which is again a very nice example to show this. And here I take the same Michaelis-Menten where S is injected and P is extracted. So if you look at the concentrations in time, the first thing you see is that only S and P are increasing. And in fact, E and ES are, ES is constant and E is decreasing in time. How do we understand this? Well, if you look at the conservation law, you see that the amount of E and the amount of ES, the sum of these two must be constant. In other words, this moiety is conserved. And therefore, E and ES cannot increase. Whereas S and P can increase. And in fact, one of S or P definitely has to increase because this moiety is increasing. And we can actually do more. We can derive the growth rates in this case by using the quasi-steady state approximation. And the idea is the same, that when at large times, if there is a lot of S and P in your system, you can treat them as slowly changing variables as compared to E and ES, which change rapidly. So you can assume that E and ES are always at a steady state, and S and P, and you can co-screen over them to get an effective equation for S and P. I don't write down the effective equation because I don't think it gives you a lot, but this is the principle that we use. And using that, we can find the linear growth rates. And furthermore, I can tell you exactly how much the entropy production rate now is a constant. Because now, again, you have this principle of converting an S molecule into a P molecule and extracting. And you can actually estimate the entropy production. And this is the line is the theoretical result. The dashed line is the simulation. And you see that it's a very good match at large time. And once again, you have this logarithmic increase in the work rate and the free energy. So what I've shown you is that under flux control, multimolecular networks can show both equilibrium and non-equilibrium growth depending on the topology. So when you had one conservation law, you had equilibrium growth. When you had two, you were out of equilibrium. Finally, I will conclude by talking about nonlinear networks in mixed control. So let's take the case of the Michaelis-Menten, and here you're injecting S and you're extracting P. And we can ask, do you see growth? And in fact, when you do simulations, you'll find that there is an initial condition dependence. For some initial conditions, you will reach steady states. And for other initial conditions, you will show growth. And the question is, how do we understand this? And this is a very interesting phenomenology that happens in these kind of systems. And the idea is, again, the enzyme moiety is conserved. So E plus ES is constant. Whereas if you look at S moiety, it can increase due to the injection, but it also changes due to the extraction. So if there is growth, the amount of P in the system needs to be below a certain threshold. Now we can again do the quasi-steady state approximation. So we assume there's growth and do the quasi-steady state approximation and see if we get a reasonable result for the growth rate. And if you do that, what you'll see is that the growth rate of S can now be written in this form. So it's IS minus, it depends on the enzyme moiety. Notice that it does not depend on how fast I'm extracting P. It only depends on the initial condition at which you instantiated the enzyme. And what is happening here? Well, the reasoning is quite simple. The system will not grow if, when you add S, it can convert H to P quick enough to extract it out. So this is the key ingredient, that to have growth, or to not have growth, S must be converted into P faster. But because E and ES are bounded above by this enzyme moiety, by the concentration of the enzyme moiety, these reaction rates are bounded above by this value, K plus 2 LE0. So that means that if the injection rate is lower than this, then all the S you're putting in can be converted to P and removed, and you will reach a steady state. And this is what I show in this example, where I'm plotting the change of this quantity, dTLS as a function of time. And you see that no matter what extraction rate you take, from very slow to very fast, you will still go to 0. Maybe slower and slower, but eventually asymptotically, you will reach a steady state. Whereas if you choose a system where the initial condition is such that this velocity is positive, then the current is faster than the extraction. And so S will accumulate in your system. And you can see it by looking at this derivative, and you see it relaxes to a constant positive value, indicating there's growth in your system. So in mixed control case, you can have an initial condition dependence, which is highly non-trivial. And we can do the same thing. Here I show a simulation. So unlike the flux control case where both ES and P were bounded, where only ES was bounded, here both ES and P are bounded, and S increases linearly in time. Once again, we can, and of course, as I said, we know what the velocity is, and we can also derive the thermodynamics. And in this case, all the three, the entropy production rate, the work rate, and the Gibbs energy, all of them increase logarithmically in time. So one final word about concentration control. We tried a lot to show that multimolecular networks don't grow in concentration control, but unfortunately, we were not able to find a definitive proof. One result I know is from David Anderson in 2011, who shows that all trajectories of weakly reversible single linkage class networks are bounded. So since we work with reversible chemical reaction networks, we satisfy this part, but we need not be single linkage class. And so the main idea, if you're interested, is to sort of nullify this condition. As I said, growth only happens if you accumulate substance, and if you accumulate substance, you're accumulating free energy. So the idea is to show that if your concentrations increase to a very large amount, the free energy actually starts, the derivative of the free energy is negative. So the chemical reactions orient themselves to consume free energy. So you can think of it as a quasi-Lyapunov function. It's not a Lyapunov function. You're not. It is not completely decreasing. But if the concentrations are large enough, then it will decrease. This was the main point. And but this, yeah, we were not able to. This is the idea that Anderson used in his paper. We tried extending it, but yeah, we couldn't. And we show numerical evidence in the paper that you cannot grow on concentration control. But as far as I know, this is still an open question. Do you have bounded trajectories for any chemical reaction network with this kind of a setup, where you fix the concentrations of some species? So with this, I want to summarize our results. So we studied asymptotic growth. I hope I defined the phenomenology well enough. We studied the asymptotics of chemical reaction networks under 3 different types of changes. And we showed that when you have influxes, as in flux or mixed control, you can have what we call asymptotic growth. And even the existence of this can be non-trivial. In flux control, as I said, because the mass density is increasing, indeed, every chemical reaction network will grow. But you don't know whether you grow close to or away from equilibrium. In mixed control, it is not even clear when, to grow, you need specific topologies. As I illustrated with the example of the Michaelis-Menten, you need this kind of bottleneck where the extraction rate, you need this kind of bottleneck where the conservation loss sort of plays an important role. Furthermore, unfortunately, I don't think I had the time to cover pseudo-unimolecular networks, but I hope I conveyed the results of unimolecular and multimolecular networks. And this thing. For prospective directions, a systematic analysis of multimolecular networks. I showed you examples. It will be very interesting to see if we can write up exact results in certain conditions. Maybe to say if you have one conservation law versus multiple conservation law, you can have different behavior. And then a second thing is transient growth. So I started initially by talking about this in autocatalytic systems. For instance, initially you have an exponential phase followed by saturation. Of course, it's not related to our work because we looked at the asymptotics versus the transient, but it is very interesting to ask if similar considerations apply, especially because there is a lot of work being done on autocatalytic networks and transients right now. Finally, combining these ideas with volume is very important. And there is work being done in the group of Kobayashi and et al., where they think of chemical reaction networks inside a vessel whose volume is expanding. And here you're interested in asking, can the number and the volume increase? Can you have growth in number and volume, basically? Yeah, that's it. I'm done. Thank you all for listening. And thank you to the organizers once again for inviting me to give this talk.
Thank you. I will stop now.